Hello everyone, and welcome back. So far in this course, we have been looking at the behavior of some different kinds of systems or objects. We've looked at particles and we've looked at solids. Particles we could basically describe using F equals ma. Solids with more structure to them, we could look at their motions using F equals ma, but then also a rotational analog of that, tau equals I alpha. What we're going to do today is start looking at an aspect of the systems that we haven't considered before, and that is the internal structure of what the system has. In other words, we're going to start looking at how the internal parts of the system might move relative to each other. With solids, we think of that as basically a rigid object that can either translate or rotate. But we're going to start looking at something else where the internal structure can actually change and change its shape, for example. This brings us to section 13, the mechanics of solids and fluids. We're going to break up our view of materials into two different kinds, solids and fluids. Let's take a look at the differences between those two things. We will divide materials into two very general different types. First, solids, which are basically rigid. In other words, they don't easily change their shape. Their internal structure basically remains fixed. They might translate or rotate, but the positions of the particles or atoms, molecules within the structure do not change. And fluids, they flow. The general description or the basic characteristic of fluids is that they can flow. In other words, they easily change their shape. We will have essentially two different kinds of fluids. There are liquids, which will flow to the lowest part of their container, and gases, which expand to fill their container, whatever the size of their container is. So, for example, solids, just a general basically what we think of as a hard object, a solid object. Well, you can't see if I do that. Okay, so something is not going to particularly change its shape. It could translate, can rotate, but it's not going to change its shape. And then fluids, we've got liquids. So here's some water, and if I move this container around, we obviously see that water always kind of flows to the bottom of the container. If I were to tip it too much, it would fall down, falling to the lowest part of the room. And gas, here I've got a gas in a balloon, just air, and if I change the shape of the container, the gas always fills whatever amount of container we have. So that's the difference between for the moment anyways, between two different kinds of fluids, liquids and gases. Now, how are we going to describe these different kinds of materials? Where there are a few properties that we'll use. First of all, when we're considering a system, we would probably like to know how much material do we have. Is that a small amount of material in the system, a large amount? Well, what we will do is first measure the mass. So what's the mass of the object? However, a mass of one particular type of material, for example, a mass of brass, is a very different amount in the amount of space that it takes than the same mass of water. So here I've got equal amounts of brass and water, about 500 grams, and we can see that the volume of the water, so don't include the beaker here, just the volume of the water, takes up, the volume of the water is much larger than the volume of the brass. So the size of the materials would depend on what the material is in addition to how much mass we have. So there's another quantity that we would like to define to go along with this that will tell us something about the volume in relation to the amount of material we have, and that is the density. The symbol that we'll use for density is a lowercase Greek letter rho. So this is a lowercase rho. And we will define the density of a particular object as its mass divided by its volume. We'll write this as m over v for short. So the mass of the object divided by the volume. The units of density will then be, what are the units? So what are the standard SI units for mass? That would be kilograms. What are the standard SI units for volume? Well, a standard SI unit for length is a meter, so what would the volume of a three-dimensional object be in meters? Meters cubed. So the density is, the standard SI units of density are kilograms per meter cubed. Sometimes we might see grams per centimeter cubed, or we might have, in chemistry, liters are often used as a volume, so we could have kilograms per liter, or grams per liter, or grams per milliliter, or something like that. Milliliter being the same volume as 1 cubic centimeter. For example, for brass, the density, brass can have different densities depending on what alloy we're talking about. Brass is an alloy of copper and zinc, and depending on how much of each, and brass could be made differently depending on the properties that you want the brass to have, it can have different densities. But for one particular form of brass, there is a density that is equal to, I've got it here, 8,530 kilograms per meter cubed. Now, let's think about that just for a second. The density of this little thing here, 8,530 kilograms per meter cubed. How could this thing have such a large number for its density? Well, keep in mind what this is telling us is the mass per volume. So if I had a cubic meter of this, it would have a mass of 8,530 kilograms. Well, what's a cubic meter? Well, remember how big a meter is. A meter is about this big. So if I had a cube this big by this big by this big, that would be a huge volume of brass. How much would that thing, what would the mass of that thing be? Well, it would be a very, very large mass, right? Because having so much brass made out of this stuff would have a very large mass, and that's why 8,530 kilograms. Well, that seems reasonable when we're talking about such a large volume of brass. For water typically, and likewise, density of things will depend on the temperature, but typically around room temperature, which is what we'll be worrying about most of the time. For water, the density is around 1,000 kilograms per cubic meter. Again, if we had a 1 cubic meter volume of water, it would have a mass of about 1,000 kilograms. There is another quantity that is often used to tell us the relative density of something, and it is called the specific gravity. And it is the density of the object divided by the density of water. So, for example, what would the specific gravity of this particular alloy of brass be? It would be 8,530 kilograms per cubic meter, divided by the density of water, which is 1,000 kilograms per cubic meter. In other words, 8,530 divided by 1,000, 8.53 kilograms per cubic meter cancel, and we get a unitless quantity. So specific gravity is a unitless quantity that basically tells us how dense something is compared to water. So what this is telling us is that this particular alloy of brass is 8.53 times as dense as water. Okay, very good. That's a very useful quantity to keep in mind. All right, let's take a look at some other properties. How does a system respond to forces? So in particular, how do solids respond to forces different than liquids respond to forces? For example, if I have a solid and I apply a force to it, I push on it, what happens? It accelerates, it changes its motion. I can't really throw that thing, but this, if I apply a force to this, what happens? It accelerates and it moves off in some different direction. It changes its motion. What about a liquid? Well, if I have some water here, I apply a force to it. I'm not going to throw this whole thing, but if I try pushing on it, if I push on the liquid, what happens? Well, the whole thing doesn't just accelerate. It doesn't accelerate downwards. It kind of changes its shape. So applying a force to a liquid gives a very different sort of response than applying a force to a solid. liquids tend to, or fluids in general, gases too. If I apply a force to this gas, what happens? It doesn't just accelerate like a solid does, it changes its shape typically. So when we apply forces to the different materials, different things happen. Well, let's try applying a particular kind of force to a solid that is not going to change its motion. For example, let's imagine I have a bar here. Well, we don't have to imagine I have a bar. I have a bar here. Here, I have a bar. And I'm going to apply a force to it, but not a force that is going to change its motion. I'm going to apply two forces. Imagine that I have this bar and I apply a force on each end in opposite directions. So one end I pull this way, the other end I pull that way. What's going to happen to the solid? Well, not much, as a matter of fact, with the amount of force that I can apply. But let's take a look at that very specifically and imagine that we could apply more force so that it actually does change the shape of the object. So here's our bar, and imagine we apply a force to the left at this end and a force to the right at this end. What's the bar going to do? Well, the response of the bar will actually depend on how big it is. The larger the bar is, the less it's going to respond, the less effect the force will have on it. The smaller the bar, or let's say the narrower the bar, the thinner the bar, the more it will respond. So the response will depend on what this internal cross-section is here. What is this area? What do I mean by the cross-section? Imagine you have an object, okay? You cut it acrosswise, and then you look at the shape or the size of that surface. In other words, if we cut it across here, what we would get is basically this shape here. For this bar, it would be round, a circle. What's the area of that circle? That's what we're talking about when we mean, that's what we mean when we say the cross section. You cut it across, make a section, what's the area of that surface? So what's the area here, cutting it across? We will define the stress, and in particular the stress that we're talking about here would be called the tensile stress. Okay, we could also push on the bar this way. Rather than pulling it apart, we could compress it, the compression stress. But either way, we'll just refer to it as the stress. The stress we will define as the amount of the force divided by the area. So what is this? This is the force per area. And what are the units of this going to be? We'll write this, I'll just write it as stress. What are the units of stress? The units of stress will be the units of force, which are newtons, divided by the units of area, standard SI unit, meters squared. Newtons per meter squared. What happens? What's this rod going to do? Well, in particular, it's going to stretch. Let me redraw this picture. In general, when we apply a stress to an object, it's going to stretch. It's going to get longer. Obviously, with the bar that I just had, it's not going to get a lot longer, but a tiny bit. Why? Well, if we think about the material as being made up of atoms and molecules, and those atoms and molecules are holding each other in place for a solid, they're holding each other in place with these interatomic and molecular forces. When we apply an external force, it kind of makes a little stretch on those internal forces, making those atoms and molecules move apart a tiny bit more so that the overall length of the rod is larger. Let's imagine that we start out with the initial length of our rod with no stress is L0, but when we apply the stress, it stretches an additional distance, delta L. We will then define the strain as the ratio of the change in the length, delta L, over the initial length, L0. Now, what are the units of strain? Well, that will be the units of delta L, the change in length, which will be meters, over the units of the original length, which is another length, which is meters, and they cancel out. So the strain is a unitless quantity. we're going to have meters over meters. Basically, the strain is giving us a fractional change in length. If this were originally 1 meter and it stretched 1 centimeter, for example, then the strain will be 0.01 meters over 1 meter, or 0.01. 0.01 would be the strain, meaning the overall length has increased by a fraction of 0.01 or 1%. You might think of it. You multiply by 100 and it tells you the percentage increase in length. Okay, what we're going to do is take the ratio of these two things.